I hope you understood that denoising is somehow understanding what you like to extract from the real world data. And it's very useful to separate the essential component and also additional noise based on models that you assume that the target signal should behave somehow. And the regulation is another aspect of modeling the signal, particularly time sequence. And it is a quite general idea. So I think a very fundamental part of the regression should be, or you should somehow have some idea about the basic regression. And I like to generalize the very fundamental ways of doing regression and also expand it to the time sequence data. Okay. So first of all, regression analysis is quite common, maybe to you. I think this is a very common idea to all of the scientific fields. So you have an independent variable. That is a quite intuitive variable like time sequence or location or such things like that. And also dependent variable. In other words, this distribution of data should be somehow described or reasoned by these numbers of the independent variable. And what is a model? I will talk about that in 5 minutes maybe. You can also easily see the line or trend based on this distribution. And this red line represents your expectation that about how these independent and dependent variables are associated with. And that is the basic idea of regression. So in other words, relation analysis between dependent and independent variables. So relation analysis. So this can be also regarded as an analysis of data. Like I said last time, this simple bar graph doesn't represent any, sequential relationship between two numbers. But when you plot against two, or with respect to two, the time expansion, or time, evolving, then this value or connected lines represent somehow very important information. Therefore, we, in this lecture series, discriminate from data and signal. Signal has to have side notation. So signal itself is a function of the independent variable. So index and also value. And the indexed value is a signal. And indices has to have order, like given by integer number or natural numbers. Okay, so this is the fundamental, ideas associated with this lecture series. Okay. So what is a signal regression? That is very simple. You can think about, or you can guess the hidden number like this. You get a sequence of number 3, 1, 4, something, 5. Then what do you suppose this is? Yes, right. So because, yeah, this is pi. Okay. You are very smart. So so the order is very important, right? Because 3, 5, 1, 4, 1, that doesn't mean anything. But if you see these numbers in this order, that's very meaningful. So you can guess what is this from the information that you extract from these numbers or sequence of numbers. So regression of signal is the problem to find the rule that generates the signal or order the data. And also the rule is useful when it is represented by a mathematical form like this, or functional form that you can calculate easily when you give them the particular number as n, 1, 2, 3, 4, 5. And once you get this, then you got almost everything. You can derive this function with respect to n so that you can calculate the, increase or decrease tendency of the data. And also you can average or estimate the expectation value by weighting this value with the distribution function. So mathematical form is quite useful. So finding this kind of form is a very, very important challenge for any data scientist. And finding the best form for the regression function is an open problem. There's no global answer because you don't know how this data has been at least contaminated with the random error. You cannot be free from the error. Therefore, if you see the lines of data like this, then it is very simple. This and this are proportional linearly. But in reality, you get this. Then can you conclude that these dependent variables and the independent variables are really associated with each other or not? Well, in this case, somehow they are. But in reality, you got a bunch of errors, a bunch of external numbers and outliers. So it is not easy always. So that's the point. Therefore, we really need to know what is the best function for describing the relationship. And if you know as many possible function sets as you can, then you can be a better data analyst because you can put several hypotheses, right? And we say that because we don't know the actual form like cosine or sine kind of things. Otherwise, we need to assume that this may be cosine function or this may be second order linear polynomial or something like that. So we need to hypothesize a rule that describes the relationship between independent and dependent numbers. Or we may say model. We built a model that under that model these relationships hold. Okay, so modeling or hypothesizing the relationship are quite similar idea or almost same. But anyway, finding the function is the final goal. In this term. Okay, very, very simple case. The motion of a particle with a constant speed. That is a physical system, okay? Very, very simple physical system. At the time 0, it is on the 1.2 meter from the origin, and it moves under the constant speed that is 0.2 meter per second. And you're going to sample the location of this particle every second. Then you probably have to have this kind of a shape signal, which should be linearly aligned. But of course, due to the errors and the noises, what you see is somehow diverged from this line, of course. But because you know that this is the result of the observation of the simple linear movement of physical system, therefore you can have a confidence that this should be aligned in a line, and lines can be somehow estimated from the least square methods that I will describe later. This is a very happy case because you know what are you observing, and physical system is quite simple. and do not do the breaking. But for instance, suppose that this is a human-related system like SNS, traffics, or highly noisy observation like 0.0001 millivolt observation or measurement under the daily activities, things like that. And even natural language or speech, those signals are quite probabilistic because of the nature of the human organs and also human intellectual system. Okay, so but anyway, I'm thinking about generation system, thinking about the system behind the data, and make it more reasonable formula of the mathematical representation. That is one very important skill that you need to have to be a good data scientist and data analyst. Okay, but we are very lucky because recent advancement of the data science itself gives us a very general way to approach the best formula finding problem. Okay, and I'm gonna formulate the process step by step. Okay, so in the physical movement system, the x0 is the initial displacement, and v is the velocity, and n is time. Therefore, displacement at second of n should be given by this simple product and also sum, constant term and a variable term. And this is said linearly correlated or linearly proportional. And this xn is modeled by a simplest linear regression. It's a little bit more general form is like this. So we don't, in this case, this is a physical value, but in this case, this is a virtual value or, general formula. That's theta 0 and theta 1. Those are parameters of the model, and n is independent variable, and xn is independent variable. So this is a most simple and general idea of describing these two variables in terms of the linear regression. Okay, so we're going to use these notations like theta 0, theta 1 when the system is first order, and when the system is nth order, then we're going to use theta 1, theta 0, theta 1, blah, 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 theta to theta n. So there are n free parameters of the system. In this case, we have only 2 free parameters, and determining these 2 parameters means that you found the optimal linear regression system for the data. Okay, and the criteria to identify the best theta 0 and theta 1 is quite simple. We can calculate the error value and minimize the error value with regard to the actual data that you have. So these black points are a result of observation. Therefore, you cannot change. This is a reality. But this line, blue line, you can change the shape. Not shape, intersection and also tilt of the line you can use. You can change by changing the theta 0 and theta 1. You can change. So you try, change, and find the optimal line, which gives you the least error. How do we define the error? That is also very simple. You can calculate the real value and also model value, and compare 2 values, calculating the displacement or diverse from the real data by means of the least square error definition. Substitute and square. and summing up to all data. That gives you the total error of the model with respect to the real data. This is very simple, okay? And if you are very familiar with the basic math, then you can also see that this is quadrature equation, simply quadrature equation. Whatever the number of the parameter are, is, because here's a square here, and if you expand this equation, then you get a x square term, theta 0 square term, theta 1 square term. That is the highest order of the polynomial of this equation. So you are pretty much familiar. I guess you are very much familiar with the quadrature equation, second order equation. In Japan, students study the general solution of the second order equation in third grade of junior high school. So, which means that the junior high school student can solve this error optimization problem by means of the quadrature function idea. Again, this is the error function. Okay, and if you plot this function with respect to theta 0, because this is quadrature to the theta 0, the shape of the error becomes like this quadrature function. And what is the minimum error value of theta 0? It's clearly here, right? Okay, the point that is that gives you zero derivative with respect to the parameter. Okay, so it's very easy and general. Whatever you use the notation, all you have to do is to calculate the total error, to derive the total error function by substituting the n sample data into this equation. And then when you got that quadrature form, then you can derive the derivatives of two independent, two free parameters, and then calculate the minimal point here. That's it, which gives you the best line that can describe the data distribution. So this is not complicated. This is not difficult. This is quite simple and general. So please well understand this idea, and then we can easily extend this idea to the general and more complicated cases based on the linear algebra. Okay. So again, I denoted the same equation here. This is the error function. That is the function of three parameters, in this case theta 0 and theta 1. And if you derive or calculate the derivatives of the error function with respect to theta 0, then that gives you like here, and by equalizing left-hand term to the 0, then you can get one equation. And you can do the same thing to the second three parameters, and simultaneously you can solve to this linear equation, and then you get theta 0 and theta 1, which holds these two equations. And you can of course rewrite that two equations in a slightly different forms, which is like this. So you see, do you agree? I don't like you to follow precise equation one by one, but please understand, or at least see the reasonable equation from starting from the previous slide, which is like here. Well, if you go in more detail, what you see, well, the difference from this and this is you have an n here, and also because you have n here, so you derive the derivative function by simply reducing the order of this and multiplied by the coefficient to the each free parameters. In this case 1, and in this case n, or things like that. So if you have time, please look back when you go back your room and confirm that this is holds. I make mistakes a lot of times, so you should be careful about to do that. But anyway, the calculation becomes like this, and when you convert these two equations into the matrix form, then you end up with this form. So theta 0, theta 1, or this vector should be determined by this equation. And left-hand side of the equation is a 2 by 2 matrix, which has the 1. It's the 1 is the coefficient of theta 1, and the average of n comes from this term. Average of n square, which comes from this term, and that is the symmetric matrix. And on the other hand, the right-hand side, you have one vector which has the xn sum or average on the first element, and n times x. That is the cross product or correlation between n and x for the second term of the right-hand side vector. And once you get this formula, then you can easily solve this formula. That is very easy. You can calculate the inverse matrix of this and product or multiply that matrix from the left-hand side to both sides of equation. Okay, so I think you are very lucky because this is quite easy in terms of the MATLAB or Python, calculation. When I was a student, we care about the solution of the simultaneous equation by a numerical method, like a Gauss-Jordan or something like that. Yes, that would be very beneficial for, at that time, the matrix like order, like matrix like 100 order or something size. So that is not big size today. Those matrices can be easily inverted. And then you can use the computer system without any fine-tuning or very big effort solving this kind of thing. So only knowing about this, that takes you to the very happy world that is where you can enjoy the regression analysis. Very simple, 2-line, 3-line codes of the Python. Okay, so again, we do the same thing, but the notation becomes a little bit more general. Okay, what we need to do is to observe the sequence of data, and if you like to regress those data in terms of the function of independent variable, which is n. So we don't see small n here, but 0, 1, 2, 3, 4, 5, those indexes are varied by n. And that is very simple again. So you organize the one matrix, which has two rows. First row is only one. Second row is 0, 1, 2, 3, 4, 5, blah, 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 blah. That is the n, x matrix, or inverse of x, a transpose of n matrix. And on the other hand, you get a y vector, which consists of the real observation value, like here. Of course, order is matter, because this is the ordered data. And then you can calculate the x transpose by x, which gives you a correlation function like I mentioned later. And also you can product theta. Theta is a matrix, vector, organized by theta 0 and theta 1 in second order case. And in general case, theta 1, theta 2, theta 3, blah, 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 blah. And then x transpose times y. X transpose is like here, and y transpose is like here. So you can multiply from the right-hand side to the x transpose, will gives you the, again, the column matrix, column vector, which has the elements, number of the element is same with the number of free parameters. So I hope you understand somehow. Yeah, if I had a pen, then I can expand this, but I cannot do that on this slide. But anyway, you can go back after going back to your room. I hope you can review the slides and confirm the derivation process. Okay, so those process gives you a general way of finding the best theta 0, theta 1 in a linear regression system. And linear regression is quite powerful because that can be extended to nonlinear but linear regression. How do I, what does it mean? So you can easily organize one hypothesis or model that each one dependent variable is given by a weighted sum of the function value of independent variable. Okay? So you can observe xn and you can observe yn, but you don't know how do they related. And you can suppose very complex function like yn is equal to 3 plus 3 times sine xn times log xn or something like that. Those nonlinear functions can be also replaced with this simple number of the x or simple observation or simple polynomials of xn. So probably you may be familiar with this kind of things. Higher order polynomial regression. I have talked about the linear regression only, simplest case, but you can extend the order of the polynomial like this. In other words, you may know mathematical expansion of the function known as Taylor expansion or Maclaurin expansion. These kind of things can be also regarded as a linear regression and further extended by replacing x squared with the general function phi 1 xn or phi 2 xn, things like that. So you get this idea? And you should be careful. Still, we call this is linear regression, even if these functions are nonlinear function. Okay, so this is another linear, and this function called the base of the base function, or things like that, or kernel function. Okay, so it is very good because we can easily derive these theta 1, theta something, whatever the value of x theta 1 is, or whatever the function form theta 1 or theta n is. That is again the completely same process. You can denote the theta vector like this, and also you can denote I mean, no, this is not a solution part, but this is the explanation part. Yeah. So this is another solution. This is looks similar to the previous one, but replaced with the function result, function output, theta 1 and theta 2, phi1, phi2, phi3, and phi m, which has mth order linear regression functions. And each individual element has a value of the function with respect to the given observation of x. And y is still the same, and you can calculate this and invert this matrices or matrix and operate it to the right-hand side, then like this. So this is completely the same process. Only difference is this matrix xt. Not a simple x0, x1, x2 kind of things, but this is the x operated by Vm or something like that. So whatever the function is, you can calculate this because x can be observed from the real world data. Okay. So I think this is a kind of a common sense for the some part of some fields of engineers in the engineering field, but I don't think this is well known to all of the field students. So if you feel this is useful, I'm very happy. But anyway, this is a generalized linear regression, and you can find a lot of versions of regression functions and get a best of them by try and error, or I don't know. So this is borrowed from a very famous textbook wrote by, I forgot his name. My God, who was the name? Bishop, yeah, what Bishop? Well, anyway, sorry. This is brought from the very famous machine learning textbook, how the regression works against to the observed data. Okay, so this actually is the original, how do I say, true data or true model of this data. Because we can generate these samples by adding small errors, which obey to the Gaussian distribution, for instance, against to the real value of the cosine, this time sine function. And how does the linear regression works for this sort of combination of error and real value? Okay, and here's a way that we use. Here's a function that we use for regression. Linear polynomial regression. Okay, and if you take, for instance, 1 for the number of free parameters, or 2, free parameters, theta 0 and theta 1, then you get a red line to represent this data. Is it enough or not? That depends on you, your application. What do you like to do? And obviously, if you increase the number of the free parameters to 4, then the result of the linear regression becomes much better to the simple regression. Okay, but still, it depends on your idea. Okay, for instance, if you use this curve, then you get a very, very small number when you extrapolate the data based on this function, like this. And also, extra range of this observation, you get a very high value. Those things are not natural, maybe to you. In this case, it doesn't so much change. It doesn't so much change the how do I say, deviation from the zero. Therefore, of course, it is not good, but not so much good like this. In this case, the very rapidly changed. So, again, this is your problem. This is your sense. Which function do you use? Okay? So please do understand that the best or least error result doesn't give you the best analysis result. So we are very, we have to be very careful about how does the data representation system will be used for the future applications. Okay? So anyway, naturally, when you increase the number of the free parameters, the fitting result becomes better and better. And ultimately, you can get a zero error case. Okay? If you use the 10 free parameters for the polynomial case, in order to describe the 10 or 9, data points, you can perfectly describe the training data with a very complex system, which has 10 parameters. Is this your final goal? I don't think so. Because real function is this, this curve, this smooth curve. Therefore, if you observe the data around here, you have this. Around here, you should have here. So the deviation from the real value and the regression value is huge. So this is obviously overtrained to this training data or a given data set, right? So again, there is a 9-order polynomial that crosses all given 9 points, but that function is not always the optimal regression, or that function is always not the optimal regression. Okay, so how can we avoid this kind of overfitting? That is very important and, how do I say, evolving idea about that. So after the word data training or data science became popular, the solution of this kind of overfitting problem has really highly developed. Okay. But anyway, one very good idea to do this is getting more data, more and more data. Okay. Even use the same order polynomial, which means that 10 free parameter model. If you get a not 9 but 15 data points, then it looks much better than the previous one. And if you use 100 observation data for estimating the free parameters, then lines almost line on real value. So if you like to use the statistics or data observations for solution, for solving your problem, please remember getting the more data is always a better idea to have the robust estimate, robust model of the real system. Okay. So one idea is always increase the number of the training samples. That gives you very good result. whatever you are using. And the second idea, although if you don't have enough data, you can impose the different idea, regularization. I also believe that you know this word, regularization. This is a very common term in machine learning. Like say, for instance, deep learning toolkit. You may need to somehow optimize the regularization term. Okay, so regularization is a quite beneficial idea of reducing the degree of freedom of the system. There are a lot of ways to regularize free parameters, but I guess simplest one is this Losso regularization. Just simply add one term to the error function, which is the square sum of all free parameters. Why? Because we like to control the order of the freedom. We like to control the number of the free parameters. Okay? In other words, if you like to keep something to be 0, so that the complexity of the model is still lower, even if we have 9 terms. Okay? You understand my point? So naturally, if you have more 0 or very small number to the theta value, then this term becomes less. Do you agree? For instance, we have say 5 thetas, theta 0, theta 1, theta 2, theta 3, 4, 5. That 4-order polynomial regression. And suppose that only third term is very large, like 0.999, and the other terms are very small, like 0.00133, something like that. Then this value is almost 1. That is very, and if you have almost all terms near to 1, like for instance, all 5 parameters has a coefficient like 1 or 0.9 or 1.3 or something like that, then the sum of those values becomes larger, right? So this term somehow can be regarded as the indices of the number of the 0 or almost 0 or disregardable free parameters. Therefore, if you add this, then the system try to decrease the number of the freedom in terms of the distribution of the parameter value. So this is a very simple idea, but it works actually very, very well. And recently, people found that this term could be regarded as a natural distribution or prior distribution of model parameters with respect to, or in terms of the probabilistic system. Actually, this looks the error, and I described this as error. But by taking the exponent of this, then you can calculate somehow Cauchy normal distribution, because you get a second order term in that is the how can I say? let me write down. Because you should be familiar with the normal distribution, which is given by exponential minus 1/2 x minus mu square or over sigma 0, something like this. And this is a normal distribution. And if you take the log of p, or natural log of p, then you get some constant term which represent here, and minus 2 over 1 x minus mu quadrature term and sigma term. So this term looks quite similar with this. Okay. So if you model the average by this sum, then it is equivalent to maximize the probability that you will see the data with respect to or with respect to this distribution. Okay, that's a very common idea. Then this term again, the quadrature term of the cedar becomes or can be regarded as the prior distribution, because this is again the cedar. Therefore, you can see the potential distribution of cedar again here, like this. Cedar. Yeah, it doesn't matter. Okay, cedar square. So this is again normal distribution, which has the 0 as a mean, and also unit 1 as a standard deviation. Okay. So actually, this least square error formulation tightly connected with the probability or log probability representation of the data by assuming that each independent variable away with the normal distribution. So this is quite general and very simple but very powerful because of that. So how does that work? Yeah. Even though you have only 9 points, and even though the order of the polynomial is quite high, like 9, you still can get a very good estimate of the real data signal when you could tune the number of the lambda. Lambda is the weight superparameter of the model that is merge product of the cedar sum. So again, so in other hand, if you cannot use if you don't use the regularization term, then the result is like this. That is not good. So regularization combined with the linear regression model, which has the general function as a kernel function, is quite powerful and easy to handle. So I hope you understand these fundamental ideas, and you can manage or you can use the tools which gives you the direct result of the regression to your observation data, so that you can further analyze and analyze the data and give good suggestion to your boss and also to your research papers. Okay. So these are first half of my today's lecture. That is a very, very fundamental and rough idea of regression analysis. Then next topic is quite not very general, but how do I say? Mostly used in a particular part of the engineering, like radiation analysis, acoustic analysis, or probably the data that has natural periodicity, but still highly probabilistic cases. But this is the first step of the sequential data analysis. Okay. So what I like to introduce to you is the linear prediction, not a regression. Okay. But prediction and regressions are quite similar, almost same. Prediction can be regarded as a regression of the future value from the past value. Okay, do you agree? For instance, you have 1, 2, 3, 4, 5, 6 m independent variables observed previously from the current data. And by calculating the weighted sum or weighted sum of the function of those values, in order to expect or in order to predict the current value, xm. This is regression, but this is also prediction. And actually, this regression can be easily realized by a digital circuit like this, which means that very simple calculation can be done. And actually, this model is quite powerful for the periodical signals, like a sinusoidal signal or Fourier transform or Fourier expansion of the sinusoidal signal or something like that. I mean periodical signal, which are very well known in a speech analysis field. But I don't go in detail about such kind of things. But there's a very beautiful theories found by Professor Itakura, who was professor here, who was emeritus of this university, and who was my former boss. And this formulation is actually implemented in all smartphones and all cellular phone systems because of the it is a very very fundamental way to compress the data for the speech. But anyway, this is linear regression. No, I mean linear prediction of the data. Regress the current data using the previous data. And if you remember what I told you, like this, linear regression of the independent variable, you can easily imagine that this can be formulated by the completely the same process for finding the optimal thetas. And that can be done also the linear algebra very simply. Like this, if you can formulate or you can organize the X matrix in this case, you can put 2, 1, 0, which represents that this is the 1 sample before, this is the 2 sample before, and this is the 3 sample before data. So in this case, we're going to try to predict the 4 sample, 3 sample ahead by using these 3 terms. Therefore, we align these data here like this: 2, 1, 0, then 1, 2, 3, and 2, 3, 4, and blah blah blah, and like this. And this is the matrix that we have to have for the right-hand equation X. And for the left-hand, right-hand side of the equation, we're going to have yt. That is the value that should be predicted from these 3 samples. In this case, 3, because the third sample should be predicted from 0, 1, 2 data. 3, 4, 5, 6, 7, and then 9, blah 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 to n minus 1. So you can see also this is predicted by this. 1 sample, 2 samples, 3 samples before this. So this is very simple operation. you just organize this same matrix and do the same thing. You calculate this and transpose of this will gives you like this. If you don't know the notation like this, Rx0, then I will describe this later. And also x times y is like this. So because all this multiplication corresponds to the, how do I say? Multiplication with the time-shifted version of the same signal. Like say x0 times x1 gives you the product of the adjacent our next time slot data, things like that. And autocorrelation function is a function that corresponds to such value. So autocorrelation function, I think I don't know how much deeply do you study about autocorrelation function, but you may have had the word autocorrelation function or correlation function. That is a very famous or popular idea of the relationship between two signals. By definition, autocorrelation function is an estimate. It's a statistical value, okay, of the random sequence. And definition is like this. That is the expectation value of the sample x of the signal x at the time point n and m. So naturally, correlation function or autocorrelation function has two indices. One is n and one is m, and xn times xm. Its expectation value is the definition of autocorrelation function. So if you knew the joint probability distribution of xn and xm, then that can be calculated like this. But usually you don't know, because that is a stochastic function. You cannot know. But in general, if you can assume that the sequence is stationary, this is very important, okay? Stationarity is quite useful characteristics of signal, but it is not always the case. Okay, so like speech, we say a, u, e, o. In the period of a and in the period of e, the signals are completely different. So you cannot assume that that is stationary. But if you cut out the segment or chunk that you only speaking about a, it should be very, very small and short period, like one more second, 1 or 2 seconds. But even that period, you can assume the signal whole self is periodical and stationary. Therefore, it is meaningful to calculate the autocorrelation function like this. Because if being stationary in terms of a stochastic process is that this value, xn, an expectation of xn doesn't change when n is changed. Okay, whatever the n, small n is, if it is stationary, then that the same. That is a strong sense stationary, and weak sense stationary is given like this: xn and the other sample that is apart from xn in k samples are stationary, but doesn't change with regard to the small n. Whatever the point is, you can calculate the relationship or product of the n and k apart sample, and that value is constant, like k. Okay, so for instance, if the k is 3, then x5 and x2, and x7 to x4. Those product remain same in the same value when it takes the expectation, when it's taken by the expectation, operation. That is the wide sense stationary definition, and usually we say stationary when it is wide sense stationary, SSS or WSS. Okay, so if you understand the definition of the autocorrelation function R like this, then you may agree with this way of calculating the LK, which can be given by the ensemble mean of the observed data of this, because we don't know the joint distribution, but all we know is the observation data. Therefore, we can estimate this expectation based on this ensemble mean, and LK can be calculated by this. So by knowing the definition of LK, then probably you may agree with the product of X transpose and X becomes or rewritten in this form. Rxs0 is the autocorrelation function, and which gives you the power of the data. I mean square value of the data. And Rxx1 is the product of x1 and x2 and x2 and x3, x3 and x4, blah 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 blah, those things. And Rxx2 gives you will be calculated by the R1 x1 x3, x2 x4, x3 x5 or things like that. So this shifted version of the data and its expectation value or average value could be used for estimating the parameter theta for the prediction function. Okay, so again, completely the same way that you use that you can use for estimate the theta, but theta represents not a regression coefficient, but a prediction coefficient. And by analyzing the prediction coefficients, you can somehow extract frequency characteristics of the signal. But that is further subject. I don't talk that in this process. Okay, here's somehow very simple linear regression system, and also like to extend the idea of the prediction to more discrete random process kind of things. In other words, Markovian system. So again, data or random process. I mean, is the or another should I say stochastic variable of the random process is a set of numbers. Those are indexed by discrete number. That's the definition. In that words, I said that the set of words or signal is stochastic. And random process is the process consists of such set of stochastic variables. Okay, so like I said in the previous lecture, this is the fundamental idea, which is that the indexed sequential data and set of indexed sequential data, and each individual set indexed data has its own distribution, and joint product, joint distribution of those n minus or large n stochastic variables gives you the probability of the random process. So this is not simple, but random process definition of random process in natural language. So it is, in other words, can be visualized like this. These all three outcomes or graphs came from the same random process. Okay, so the random process gives you the probability of each individual set of lines or signal. Okay, and these three observations are somehow probable from the given random process, but of course the shapes are completely different. And what is this? 9:30. Yeah, but if you observe a lot of random variables, I mean a lot of observation from the random variables I'm sorry. Oh, that's a mistake. So this is actually this line, this smooth line was the original line that I used for generating each individual random process like this. So I simply add a small variation of error to this original smooth curve, which is of course stationary, deterministic. But by adding small errors, then you can get some kind of error. And it gives you a random process. Okay, so what I'm talking, well, sorry, I'm not so clear about the definition of random process, but that is not so much important in current research. Okay, so most important fundamental knowledge on a random process is joint probability and Bayesian rule. Okay, I know you studied about the Bayesian rule and Bayesian correlation between two variables. Like for instance, the joint probability of A and B can be calculated by the product of the conditional probability of A under the condition that you gave, the B is given, times the probability that you observe B. Okay, this is a very simple and fundamental correlation. And when you calculate the sequence of the discrete random variables like a natural language, then this Bayesian rule can be expanded, can be applied for calculating the long sequence probability. Okay, for instance, the joint probability of these five, probabilistic or stochastic variables are not easy at all. Suppose that this is a word and this is a natural sentence, like I would like to go somewhere. I would like to go somewhere, okay? So the probability that you observe the word I should be very, very small because we have a huge vocabulary that we use every day, like 1,000 or tens of thousands. And I would like to go. The variation of the 5-word sequence is huge. 10,000, 10,000, 10,000, 10,000, or 10,000. We cannot, calculate such a, huge space of random variables probability. So we have to have several models that represent the sequential correlation, a sequential generation of such random variables, particularly for the natural language application. Okay, so the one idea to model such sequential correlation of these 5, independent variables is the Markovian model. Okay, but anyway, I think you may also know chain rule. Chain rule is the generalized version of the Bayesian rule. Okay, so we apply a chain rule to this 5-word sequence. Then you can calculate this 5-word sequence joint probability by the product of 1, 2, 3, 4, 5 terms. First term is W1, and second term is W2 given W1. So product of this and this gives you the W1, W2, right? And then you can, you can multiply W3 given W1 and W2. Then you can get a third term, and W4, W1, 2, 3, W5, W1, 2, 3, 4, 5. That means 4, which naturally gives you this product based on the Bayesian rule. It is very nice because in this case, you can only think about I would like to go. Okay, the probability of I, probability of would, under the condition that the previous word is I, or something like that. Okay, but still you need to know the combination of these 5 words because this is the conditional probability. Therefore, if you change the 4th word, second, third word, the result will be changed. But when you put the Markovian assumption of this sequence, you can drastically change the formula to much more simpler one, which is given by the next slide. Okay. Instead of calculating, or instead of using the very long history to give the condition of the final word of W5, you forget about the long before. You just remember the previous case. So this is assumption that these 3 terms I would like doesn't affect the conditional probability of go, but only 2 is effective to the probability of W5. So we replace this long history probability to the very short history probability like this. So go follows word 2. That is the, of course, simplification and also the application and approximation. But there are a lot of real phenomena that the condition or history is quite short that affect to the probability of the observation. So this is so-called Markovian assumption. And based on the Markovian assumption, you can calculate this multiple product with this very simple 5 times probability. And good thing of you is that all these things are 2-term joint conditional probability. Therefore, you can use the same probability function for this and this and this and this. So if you have the probability, a set of probability values for the pairs or sequence of 2 words, then you can calculate every combination or sequence of a natural language based on this conditional distribution. And this is called the bigram. Okay. yeah, we call the unigram, bigram, and trigram. Natural. And when I was in a company, I quitted that company in 1995. The trigram of the natural language is very difficult to estimate because of the capability of the computer powers, and also we didn't have enough resources or language resources to estimate this. But currently, like Google, they have a huge computational power and huge natural language resources. Therefore, they can calculate a very, very long history conditioned word sequences in order to provide the Google translation services, or also predictive search, or also a lot of another natural language applications. Huge, like 5, 10. And imagine that combinational space is huge again. So like natural language in Japanese, in terms of the word, we have millions of word vocabulary for the everyday use of the Google services. They preserve all combinations. That's a huge memory. Of course, they have a good way to expand and compress the data representation. But anyway, these approximation that the probability of the word is conditioned with a limited number of history is quite useful and applicable, whatever your idea is. So it can be also applicable to the numerical sequence, and also I don't know, whatever you use the discrete variable. So how can we estimate the trigram, bigram, or grams? It's quite simple. Just count out. Okay. So the probability estimation can be done by simply calculating the ratio that you observe the all combination that is that has the Wj in the second term against to the all combinations that the word Wj will appear just after the word Wi. So in this case, the total Wj observation, and this is the number of the count that the two particular sequence, two particular words are here. Just counting, okay? But please be careful for counting the data. There's a big, big hole that you easily, fall into. The lacking observation problem. Okay? So please be careful about this. Natural language has, say, thousands of words, okay? But when you collect your corpus or training data and calculate or count the occurrence of the 1,000 data, probably you have tens or hundreds of words that you don't see your corpus, your data. Then you can naturally say that, okay, we don't have any observation about such particular word. Therefore, we can put probability 0 to the data. That may be, but that sounds maybe natural, but it doesn't work, because that very rare event can easily happen in the next corpus. Okay, this is another problem of overtuning. You have a training text, and you estimate the probability based on that text, but still the different text has different characteristics, and also the rare event particularly. So there are very good ways such things. One is the discount method. So you count in the real corpus 180, 50. So in total, you have 250 observations and 0, 0, 0, 0, 0. But if you knew that there are 1, 2, 3, 4, 5, 6, 7, 8 symbols, and only 3 symbols are observed, have been observed in your corpus, then you discount these 80, 70, 50 by small amount, like 5 or 3, and then distribute those discounted counts to the unseen data. This is somehow, making a floor value smooth the distribution. But this is quite commonly done for estimating the n-grams. And I think this is also very useful for different applications rather than natural language. Okay, so please, have something please have some ideas from this figure. Okay. Only you see in your your test corpus or your training corpus is not all. There are natural symbols there, but you accidentally didn't observe this data. In that case, you can discount this observed data and give these probabilities to those unseen data to make very robust model of the data sequence in this case. So anyway, n-gram has very powerful tool actually used in the a lot of sequential analysis problems. So I hope you may also be able to use this technology. Unfortunately, we don't have very common learning algorithm for n-grams for various languages, such like TensorFlow or Caffe for the deep learning. But you can also Google the n-gram tool. There are several, not so sophisticated, but easy to use n-gram. And also, if you are dealing with the English text, then you are lucky because Google provides n-gram of the natural English text for the research purposes. Therefore, you can use that. But anyway, this is a typical and fundamental idea of dealing with the sequential data of the discrete variable for natural language. Okay, so this is the final slide of today. I talked about regression analysis first, and assumption and modeling. How does those words mean? That was the first subject. And also, I reviewed and generalized the basic way to estimate the free model parameters based on the least square minimization. And then I mentioned about controlling the complexity of the model by changing the order of the regression or by adding the regularization term. And then I shifted to the second topic, which was the probability modeling of a sequence in a Markovian modeling and also n-gram probabilities. Okay, so sorry about very, how do I say, chunked topics, and I know that I think my English is very bad, but I hope you get some idea and keywords to study about signal processing and also applying them to the your own real social or engineering problems. So if you have any questions, I like to take and answer here or discuss. Otherwise, I am going to close this lecture. Okay, thank you.